Swayam Prabha. Digital India. Educated India.
Okay, welcome back. So, today I want to discuss the parameter determination of the induction motors, equivalent circuit. We want to estimate the parameters from actually instead of saying estimation, I think probably the better word would be determination, because we are doing tests. Estimation usually means we are not sure, there may be still something unknown, so to say, that is there. We are actually doing tests and then directly measuring it. So, parameter determination from basically two tests that we are going to do it. One for induction motor, one is known as the no load test, and other is known as clocked rotor test. So, these sort of that induction motor is a generalized transformer. We usually equivalence it with a generalized transformer. So, for transformer we had open circuit and short circuit test. Corresponding version here is no load and blocked rotor. So, these are the corresponding two tests, and if you recall the equivalent circuit of a induction motor, this is JXL1 leakage reactance of the primary winding, resistance of this, magnetizing impedance which is much lower than transformers, we have seen that also, Rm, and this sort of is the equivalent of what we used to have in the transformer also, and this side the rotor which goes through the air gap, you have R 2 dash by S, J x 2 dash, dash is, what is dash? Referred to primary, I mean to the supply side, primary. So, this side is our secondary, this side is primary, and we connect the supply here, right. So, phasor we usually angle 0 is what we take. This will be your no load current, so to say. This will be your I 2 dash, and this current is I 1 dash. So, these are this is what is our equivalent circuit. What was S? S was slip, and slip depends upon what? Slip depends upon speed of rotor. So, it is obviously a variable, it depends upon the speed of the rotor. So, then when I say I want to determine the parameters of an induction motor, what I mean is I want to determine not slip. Slip is like when we operate the machine, we will measure the slip, but what I want as parameters is R1, XL1, R2 dash, X2 dash, Rm and magnetizing impedance Xm. So these are the uh, these are the these are the quantities that we want to determine when we say we want to determine the no load test. So, to set some uh, notations, let us say that V L N L is V 1 sorry V 1 N L is the line to neutral, and remember induction motor is a 3-phase machine. So, therefore, this is line to neutral voltage in volts. I 1 N L, my treatment is from Fitzgerald Kingsley chapter 6, basically that is the I found that one of the most detailed treatment on the parameter test, and PNL is the total 3-phase. If it is 2-phase, N-phase also you can generalize it, but I will generally discuss it for a 3-phase machine. So, the total 3-phase or polyphase electrical input power. So, how will you how can you measure this 3-phase total electric? You can have 3 wattmeters in each phase, line to neutral, or you can have 2 wattmeter method also. I think I have discussed 2 wattmeter method. For a balanced circuit, you can measure 3-phase P 3-phase power by so if this is the line here, then this is the center line. So, I have current coil and I have potential coil, and I have here the second wattmeters current coil, and I have the potential coil here, and this is the W1 and W2, and I can measure P1 plus P2 to be W1 sorry not P1 plus P2, the 3-phase power as for a balanced circuit as W1 plus W2. But as I said once earlier also, I think I have discussed it. This is of course good thing to discuss, but usually I would always recommend to you to use 3 wattmeters. A bit of redundancy in the data is any day better rather than saving 1 meter, because let us say 1 meter has some calibration error or something like that, you will not come to know if you use minimal set of measurements. So, you see your phone, you say so many cameras are there in it, so many sensors are in there, and the more is the redundant thing, the more you can apply your filters properly to remove errors, biases, noise, whatever. So, I think that era where we used to talk of minimal instrumentation and very smart way of connections is academically not academically, intellectually very pleasing, because it gives you so much to learn. But best is put 3 meters, 3 voltmeters to neutral, 3 so 3 wattmeters properly to neutral, and then measure everything. So, you can verify that each phase is balanced. Maybe if your supply voltage is not balanced and you are assuming supply voltage is balanced, and you get your meter readings and so on and so forth. This whole theory was based upon meters being balanced and all that kind, supply being balanced. Induction motor parameters usually will be balanced, but even that why should you assume? But 3-phase, if some fault has developed inside, you won't even know. But if you do 3-phase instrumentation, you will know supply is balanced, you will know your motors are drawing balanced current. Won't you be happy seeing all that? So, I I will stick to this, that one should use redundant instrumentation and make sure that you get everything, you know. So, measure all the 3 currents, check they are balanced, 3 line currents, check that they are balanced, measure all the 3 voltages to neutral, check that they are balanced, measure power in all the 3 phases, check that they are balanced. Anyway, power, if supply is balanced and motor design is balanced, then the 3 phase powers, active as well as reactive, per phase will also be balanced. Why? Because together they just act on one node which is connected on the shaft. So, automatically it will get distributed equally among the 3 phases. There is nothing, no rocket science really required about it, but one should measure all of that and then go about it. Now, this input, so let's start with there is one more thing that which I think we did not do that in transformer, but one more thing that we need to do here is, for resistance R1 of the stator winding, DC resistance, because AC has skin effect also. So, so therefore, we talk of DC resistance. Skin effect is basically saying that if you pass a AC current through a bulk conductor, you must have studied it in physics, you will also study it in power system. Then current, like the DC, it does not distribute uniformly throughout it because of the flux linkage, eddy currents and flux linkages which are set up. Current usually remains in the to a skin depth, you know, skin depth is very small. So, it remains on the outer shell and does not exponentially sort of the current density decays down as you go towards the center, and within a skin depth, most of the 2 or 3 skin depth, most of the current will be packed. So, therefore, what happens, effectively the current density becomes larger. So, if the its cross section area becomes, effective cross section area becomes smaller, current density becomes larger. So, therefore, AC resistance usually is higher than the DC resistance, and higher the frequency, higher is this effect, lower the frequency, lower is this effect. So, here we will measure first the DC resistance of the from we can measure separately, we should measure the stator DC resistance at around operating temperature of the stator, because resistance also, you know, if you really want to do accurate parameter estimation, then resistance is always a function of temperature, and so accordingly. So, one way of handling this, see, skin effect is a very serious issue in power system, but here in motors what we can do is, we can have parallel small conductors. When you have parallel small conductors, then the efficacy is that current distributes in so many parallel strands, and then that way you get a much closer value to a DC resistance. AC resistance can be brought closer to a DC resistance than the AC resistance. Okay. And now, what I will do is, line to neutral voltage is going to be, if you are measuring 3 line to line voltages, then it will be UVLL by root 3. So, for a 3 phase machine. Now, what we need to calculate also, so if you look at this no load input power, that if you look at that no load input power, it will be made up of primarily 2 components. One is the 3 times I 1 NL. What is it? The line current, it is written it in volts, it is in amperes. This is magnitude basically. So, 3 times square R1, the resistance of the this thing. So, this is the 3 phase stator copper loss plus predominantly the rotational loss, is it not? So, these are the 2 main components of it. The induction motor will be running very close to the synchronous speed at no load. So, the rate of change of flux which is seen in the rotor is going to be practically negligible, and later on we will also discuss a bit about how to separate out the components which are related to RM, the hysteresis and the eddy current losses which will be there, but for the time being we can consider it bundled into the rotation loss, which is friction, windage, and then basically PNL can basically be calculated. So, what from this equation what will I get? This implies P rotation can be calculated. Why? How I have calculated it? Measure this separately. This current is measured, the line current is measured. So, 3 phase machine I have taken, calculate this stator loss. Once you subtract the stator loss from here, what goes in as P rotor is all which is this side, but slip is close to 0. In the no load condition, slip is close to 0. So, you can imagine that there is like a as good as a open circuit here. You can sort of imagine that there is sort of open circuit here, because S going to 0, R2 by S goes to infinity, a very large value. So, practically no current flows in the very little or no current flows on the rotor side. So, whatever current that I am measuring here basically gets diverted into this thing, but these losses right now I am not separating. So, this loss I am right now clubbing it with the friction and windage itself. That is to begin with, that is a good way to start out. Then basically whatever this current is flowing is creating basically this copper loss, which is this thing, and then all the rest is like transferred in the overcoming friction and windage losses in the associated with the rotor. So, this is what is going to happen. So, one piece of caution that you should do this, measure these after a time gap, that is to say that the rotor should settle down in its steady state operation speed, because friction and windage and the bearing should become smooth, you know. So, immediately start on measure, switch off, do not do that. Start the motor, keep it running for some time. So, the windage losses and everything has settled down, you know, bearings have become smooth, there is no instantaneous overcome friction to be overcome and all that. Then measure these losses, and you can, once you will know these rotational losses, then we can treat these rotational losses as constant, because usually the induction motors operate in a small speed range near the synchronous speed. So, the rotational losses can be considered almost constant, and then they will be required for doing the efficiency calculation later on. Now, suppose I want to measure the friction and windage loss separately. Let us say I want to measure the friction and windage loss, separate out. So, P rotation I want to separate out into the RM component now, and actually the friction and if I separate friction and windage loss, then from this component that I have measured here, this which I have measured, if I separate, this is made up of friction and windage loss and core loss. So, if I separate this out, calculate this out, determine this out, separate this out, then I can subtract it from P rotational and I will get the core loss. So, I can calculate, that is what I am talking about right now. I am just giving you an idea. Usually RM is not modeled, RM is this is not really that important to model most of the time, and loss which is happening in the core is usually bundled with friction and windage loss. But how it can be done, I am discussing now, you can do it if you need. So, what we need to do is, there are two ways of doing it. First is method 1, what you can do is keep stator unenergized and connect a motor to the shaft of the rotor and bring the rotor to the steady state speed, whatever is its rated speed, 3000 rpm, 1500 rpm. If it is a 50 hertz 2 pole motor, it should be brought to 3000 rpm. If it is a 4 pole motor, it should be brought to 1500 rpm and all that. So, bring it to its rated speed. Then measure the input power of that is required to measure the from the external drive and measure the output power of the drive, not the input power. Measure the output power input power means, of course, the losses, stator losses, core losses, all of that, whatever other thing you are using, it could be another induction motor, it could be DC motor, whatever you have put, all that will come. What I am interested is in the output power, and I measure the output power there. Then that output power is nothing but the actual rotational loss which I talked of here. So, P to that was which was written as the P rot earlier is actually speaking P rot true plus core losses. So, if I measure this from external drive with my original induction motor unenergized, because once it is unenergized, core loss will not happen in it, it is just a dead load on the external drive, and then I measure the output power of that external drive, then basically I truly I have measured this, and then this I subtract from whatever was the P rod that I have written earlier, subtract it from there, and I will get the core loss which is associated with the induction motor. So, I can separate it out. Another way of estimating is, suppose you know the moment of inertia of the induction motor, then what you can do is open the motor is operated at the no load, bring it up to the rated speed, and then suddenly disconnect the supply, So, the supply is gone. So, what will happen? It will start deaccelerating, and the deacceleration is due to friction and windage. Supply is gone. So, core loss is not being there now, and this will be P rotation by the omega n. So, to measure P rotation, all you need to do is, immediately after you have disconnected, you have rated speed, you have already brought it to the rated speed. So, you are just measuring the rate of change of speed d omega by m by dt, and from this you can also estimate the rotational losses. So, this requires you to know from the manufacturer or some way, you need to know what is the moment of inertia of the motor, then directly you can estimate it. Once you have estimated this, then essentially now what we are saying is the loss which is associated with the core is the PNL minus the P rotation, which we have now separated out properly, minus 3 no load current square times the resistance, which also we have separated it out. So, therefore, you know this is also, all of these are watts, 3 phase value. That is why this please note that this 3 multiplier factor is coming because of that. So, now I have got that, and from here I can measure R1, which is the resistance of the resistance of it. How can I measure per phase? See, um, roughly speaking, see this R1 is very small value, right. This Rm is a much large value, and then of course, there is a Xm sitting here, and there is a this thing also sitting, XL1 also sitting here, and the current is flowing like this. So, the predominantly the voltage drop is happening here, because these values are large, these values are much smaller compared to this. So, you can assume that whatever V1 NL, the no load voltage that you have applied, is as good as applied here, because the drop here is negligible or very small fraction. So, therefore, you can assume this. If this VNL is applied here, then the current which is flowing through the resistor is going to be how much? V1 NL divided by Rm, and current into voltage in the resistor, the voltage across the resistor times the current which is flowing through the resistor will be the loss which is happening in this effective Rm resistance, and this is a per phase value. So, for a 3 phase system you multiply it by 3, and if you multiply this it by 3, then you will get basically the P core, which we have separated it out here. So, therefore, I will get I can write Rm, actually another notation for it is Rc, core loss, can be written as 3 V1 NL square divided by P core in so many ohms. I have measured Rc now. So, what I have got? I have got the resistance of the stator winding, I have got Rc. Now, what is remaining in this side, in this circuit to get? I have to get this X leakage 1 or X1 and the Xm. Now, from here onwards, what I am going to do is I am going to assume that though we know that Rm is directly taken care in the friction and windage losses, and this is just Jxm. So, this is just the magnetizing impedance. So, all the calculations become simplified. You can always rearrange and work out the expressions if you want to also model Rm separately, but the standard practice is core losses can be moved because they are predominantly required for efficiency calculation. Other than that, they may not make very significant impact. So, they can be considered to be part of an approximation, part of the fixed windage and friction losses, and core losses all are kept separately. So, this is what is my circuit. So, now look at this, suppose I have this. So, here this circuit is equivalent to R1 here, and this is going to be basically the self inductance as measured, which is going to be equal to the leakage of the primary X1, we used, I think X1 is what we had used earlier. So, X1 plus xm. This is what we will get. Now, we have measured V1 NL. So, V1 NL divided by this current I1, the I1 NL, the no load current, this will be basically equal to R1 plus Jx1, R1 plus Jx1. Now, what is my V1 I1 star? That is the power which is going inside this machine, which is V1 divided by V1 by V1 divided by, I am taking V1 as the I am taking V1 as, what is it that I am taking? I am taking V1 as my reference. So, therefore, V1 I1 star will be V1 divided by R1 minus Jx1, which is same as V1 square R1 plus Jx1 divided by R1 square plus x1 square. How? By multiplying with the complex conjugate of R1 minus Jx1 on the numerator and denominator. But what is this? This is the square of the impedance Z. This is basically Z square, this is V1 square. So, the ratio of this is the basically I1 square, the current square, magnitude square of the magnitude of the current, times of R1 plus Jx1. This is equal to P1 plus Jq1. So, therefore, I can say that P1 is nothing but I1 square current magnitude, not these are phasors, these are magnitude currents. When we do normally connect a meter there, what you measure is only R1, what you measure is only amperes RMS value, phase angle you do not get it, you have to calculate it. And similarly, Q1 will become equal to I1 square x1. So, you got this one very interesting formula here. This formula of course, all of us know, but this is another interesting formula, that we can say that in resistance I1 square R1 watts of loss is happening, and in this volt amperes reactive, I1 square x1 is the loss which is happening in the inductance which is connected with it. So, probably this is a formula we are seeing it for the first time, but Q1 can be simply very analogous to R1. We can write it as I1 square R1 as P loss is I1 square R1, and reactive power loss you can call this, first one you can call as active power loss, second one you can call it as reactive power loss, will be I1 square x1. So, from my instrumentation I have measured the volt V1 I1 plus second VA phase to neutral plus let's not worry about this. Let's say from I have measured the line current and I have measured the voltage current. So, whether I do it using whichever way, basically what I am saying is from my this thing, I know the 3 phase volt amperes, because I have instrumentation done for the line voltages or phase to neutral voltages, I have instrumentation done for all the 3 currents. So, what line current? So, therefore, I know the line to line voltage, I know the line current, and and if I do just root 3 times of this, I know the 3 phase apparent power, which is volt amperes, which is being drawn by this. And this 3 phase S square is basically at the no load, just NL to show that we are doing it right now, the test on the no load will be equal to what? Will be equal to P no load square plus Q no load square, that is the definition of the apparent power. So, I will get basically that this, either you do it like this or you do it as 3 V1 NL, I line NL. Line to neutral voltage if you have taken and line current you have measured, then you calculate like this, or line to line voltage and line current if you have measured, you calculate it like this. Whatever it is, this number is known. This number already measured, all the previous discussion we have been having around PNL square. So, therefore, what do I get? I get QNL as square root of S square minus the P square, and this S can then basically be written as, so per phase how much will be the QNL? It will be 3 and divided by the current square. Why divided by the current square? Because I just am now using this per phase value I calculated by dividing this by 3 divided by the square of the current, and I will get my XNL, and this XNL is basically x1 plus xm. So, I have still not separated out x1 and xm, I have basically got this value, and usually the power factor at the no load is very small. So, therefore, the reactive power component QNL is much greater than the PNL. So, if you want to make an approximation, you can also make this approximation, or rather when you do this in laboratory, you can try to check the validity of this approximation, that take voltage line to neutral divided by current, whatever you get is actually square root of r square plus x square, x11 square, but because r is much smaller than this, approximate that itself as the XNL. So, you get the XNL, but you have not still separated x1 and you have not separated x1 and xm yet, that part is still remaining. That we can consider to do when we come to the next set, which is known as the blocked rotor test. So, blocked rotor test will be done, the blocked rotor test will be done with the rotor blocked, you do not allow, clamp the rotor, do not allow it to move, that is what is meant by blocked rotor test. If you do not block it, what will happen? It will start rotating, it will go towards your no load thing. So, I want to and remember in the first task no load test, I said secondary circuit is as good as open circuited, that is why I could not dive deep into what is happening with R2 dash and X2 dash, because slip coming close to 0, it had got open circuited. Now, in the blocked rotor test, basically I want to dive deep into parameters of the secondary side, R2 dash and X2 dash, and to do that dive deeping, I cannot allow S to go towards this value. I cannot allow S to go towards 0. So, best is to hold the rotor at standstill, so that the S becomes unity. Then 50 hertz current will also start flowing through the secondary side, and you can do the parameter estimation, you can get dive deep into the parameter estimation. Now, there are two small points that there are two small points that I want to mention here, that leakage inductances in induction motor are dependent upon operating condition because of saturation effect. See, the transformer was a very static device, right. So, there was nothing to worry about that, but in the induction motor there can be some saturation effect. So, you should try to create a condition in the rotor which is very close to how it is actually while measuring these parameters. So, you should try to create conditions on the rotor side which are very close to this thing. So, operating leakage reactance is dependent upon operating conditions. Why do I make that statement? Because of saturation effect. Why do I make this statement? Because the saturation effect is also somewhat frequency dependent, because the flux patterns will change according to the frequency dependence. So, it is better to create a frequency also in the rotor side currents which is similar to what will be there in the operation time, what is there in the operation time. So, one thing which there is a IEEE standard 12 which deals with this 112, IEEE standard 112 which deals with it, and it suggests that blocked rotor frequency, blocked rotor test frequency can be 25% of the rated frequency. Another thing that you should take care uh, is that the currents that you are sending also should be comparable to the rated current value. Where do you want to, suppose you say that I am more interested in parameters close to to the starting current, I want to calculate my parameters with the conditions which correspond to starting condition. Then you can just connect rated voltage and do your test, because you connect a rated voltage, the proper starting current or whatever is the condition according to the starter that you are using, whatever are the starting conditions, fix that voltage line to neutral according to that, and then do your measurements. Or if you are trying to get these parameters close to your operating condition, then the starting current is much higher. Starting current is much higher than the rated current, because the slip is reduced during the rated condition, rated operating condition. So, reduce also the voltage, reduce also the voltage, not only frequency, but also the voltage which you are applying to the terminals of the motor. So, let us say that V1BL represents the line to neutral voltage, I1BL represents the line current, and PBL represents the 3-phase electric input power. See, I write everything in units and sometimes I make mistake also. This is amperes. This is a good practice to keep writing units always. This is in watts, and this time we also have to keep FBL as the frequency of the blocked rotor test, which is in hertz. Now, as we did earlier, I can calculate QBL. The blocked rotor reactance can be calculated from the blocked rotor reactive power. So, I can calculate this, right. So, from the power which is going inside, so I know what is the PBL, that is the wattmeter reading, square it and subtract it from the apparent volt ampere square, and you will basically get the QBL. Now, this QBL is going to be what? This QBL is 3 times V1BL plus I1BL, I am sorry, not QBL, SBL, है ना? This SBL, the apparent power S is 3 times of this, and this is actually, I should have said this first. First I do this, then I subtract this, then I get this, and then once I have got this QBL, then I divide it by 3, I multiply it by I1BL square, and I get the reactance value, which corresponds to what frequency? FBL frequency. So, therefore, I scale it down to 1 hertz, which, and then bring it back to the rated frequency, and I can calculate the XBL, whatever is that XBL. What is that XBL? We will see that more carefully, but the blocked rotor reactance, for the, we need a name at least for whatever we are doing, and this is my blocked is it not? This is the reactance that I have calculated. Now, it has many components, because there is a XM, there is a X2 dash, there is a X1, there are 3 reactance components sitting there, and it is series parallel circuits. There are resistances also, so they will also come and play a role. So, there is some total of all of that, we need to still worry about that, but whatever finally we do that sum total, we that 3 components, all of those circuit components come together and present themselves at the input as this blocked impedance. Now, what about the resistance? Similarly, we get one resistance, right? At the end of it, what I am saying is, I have this supply connected, I did the block test, I measured voltages and currents, I finally, whatever is that detailed circuit that I had earlier here with S is equal to 1, with S is equal to 1, I have to parallel this, then get this will become one equivalent, that will have one resistance, one inductance part, reactance part, then the resistance part will add with here, that parallel combinations, reactance part will add with here, and in that sum total whatever is coming out, that is coming out to us as this and JXBL. And this JXBL we just discussed how to calculate that. Now, we can also calculate the RBL also, as in the same way the PBL divided by 3 times I1 BL square, and here because it is resistance, there is really no direct connection with frequency. So, we do not need to do any frequency scaling associated with this. Okay. Now, what is my Z blocked? This Z blocked is what? This plus J this. Now, what is that Z blocked? Basically, first what do you encounter? You encounter the primary winding resistance R1 and the leakage reactance of the, which I am calling it as X1 in the transformer circuit. So, that is R1 plus JX1 is first that I encounter. Then I get a XM branch in parallel, and because I am doing it on S is equal to 1. So, I get R2 dash in parallel with X2 dash, and that comes in parallel with this XM. So, and that whole thing together, this whole thing here, S is equal to 1, this is neglected. So, this in parallel with R2 dash plus JX2 dash, this whole thing together presents in series with R1 and JX1, and then that gives me the net impedance. So, therefore, it is R 1 plus j x 1 plus R 2 dash plus j x 2 dash in parallel with j x m, and I am not going to do the complete detailed calculation. This part I am leaving it to you, but you can show that this is nothing but R 1 plus R 2 divided by x m square by R 2 dash square plus x m plus x 1 square, this is the net resistive part, plus j times of x 1 plus x m R 2 square plus x 2 x m plus x 2 divided by R 2 square plus x m plus x 2 whole square. So, if you simplify, this is R 2 dash, this is R 2 dash, R 2 dash, R 2 dash, x 2 dash, yes, this is R 2 dash, yes. So, this is what is going to present yourself as this thing, and see, because the x m was in parallel with R 2 dash plus x 2 dash, when you do take that equivalent shows that resistance part reflects both on the reactance side also, and the reactance part also reflects on the resistance side also. So, this is because of the series parallel combination of R plus j x branch with j x m branch. So, it is not very surprising. Now, here of course, we have already made an assumption that all the reactances are at their rated values. We can also make one very interesting observation and assumption that R 2 dash will be much less than x m, because the magnetizing impedance is, even though the rated currents in the no load current in the induction motor is higher than the no load current in the transformer, because there is a air gap sitting there, and air gap requires more magnetizing current to flow. So, x m is also a bit lower than what you may see in the transformer, but yet it remains the fact that the R 2 dash or the resistance of the will be much less than the x m, the magnetizing impedance. The magnetizing impedance still dominates. No load current is much less than the full load current. So, what we will do is, we will ignore therefore this here, and in this numerator also here we will ignore this, and here we will ignore this. Why are we ignoring it? Because this number is much larger than this number. Similarly, here also this number is still going to be much larger than the R 2 dash number. So, if you do this this thing, of course, this somewhat attuned, this is further multiplied by x 2 dash, so long as that is also greater than 1, even bigger number you will get. So, what will happen is, ZBL will turn out to be R 1 plus R 2 dash x m square divided by x 1 x m plus x 1 whole square. So, I can actually write this as simply as this plus j times x 1 plus, now again here this is gone. So, it is only this term remaining, this is gone. So, only this term remaining. So, again this cancels with this, and so I basically get this as j x 2 j x 2 x m x 2 dash comes from where? So, j, sorry, let me write it first completely, j x 2 dash x m divided by x 2 plus x m. So, you can now check here that this x m is sitting here, this term cancelled out with this, leaving you x 2 dash which came here, divided by x 2 dash plus x m which came here. So, I have basically now come to this conclusion that R B L is R 1 plus R 2 x m divided by x 2 plus x m whole square, and R B L is known to me, and at the x B L brought to the rated frequency is x 1 plus x 2 x m divided by x 2 dash plus x m. Now, here again you can see that I can therefore write x 2 dash now, x 2 as, from here I can write x 2 as x B L. I will transfer this to this side, bring this here and bring it down here. So, I can write x 2 dash as x B L minus x 1 divided by x B L x m, sorry, x m divided by x m plus x 1 minus x B L, and I can write R 2 dash also as R 2 dash also by taking this here on this side and remanipulating it. I can write it as R B L minus R 2 dash minus R 1, sorry, minus R 1 R minus R 1 into x 2 plus x m divided by x 2 dash by x m divided by x m square. So, I have manipulated both these equations in this form, and a small one more thing I have done here that I need to explain to you, that see this x 2 dash is the this x 2 dash I have this expression is what I have basically simplified. Yeah, so this is no, I do not think I need to explain this any further. I think this is clear enough, except for the fact that instead of x 2 I have written it as x 1 minus x B L. So, x 2 instead of so x 2 I have written it as x 1 minus x B L, and I think that follows. I think you can follow it up from the previous part. Okay. So, now what we need to do is what we need to what we need to now worry about is if we substitute. Okay, so let me we need to now get a expression for x m. So we have to calculate the expression for x m, and for that if I take this equation, if I take this equation that x n l no load test is, which was the self inductance measured, is x 1 plus x m. If I substitute this in this equation here, in this equation here, then I will get that basically if I substitute rather x m here. So, if I substitute for x m as x n l minus x m, then I will get that x 2 dash coming from this equation, I will get x 2 dash as x b l minus x 1 into x 2 x m, I have written it as x n l x 2 dash. So, I have substituted for x n l minus x 1. So, x n l minus x 1 and the denominator will turn out to be so x m is substituted as x n l, x m is substituted as x n l minus x 1 divided by the denominator which is sitting here. Slight things you have to just carefully work it out, x m plus x 1, so we are substituting for x m as x n l minus x 1 plus x 1. So, therefore, x 1 will vanish and this will become x n l minus x b l. So, this will become x n l minus x b l. Now, the point is we are still not able to separate out what is the distinction between x 1 and x 2 dash. This is not very apparent from here. So, what has to be done is usually this empirical distribution is used. This empirical distribution has to be used here, and the standards specify, the IEEE standards specify motor class into A, B, C, D and wound rotor. This is standard IEEE standard 112, as I mentioned you, 112, and this says that for class A motor with normal starting torque and normal starting current, if this is x 1 plus x 2, what fraction should be used for x 1 and what fraction should be used for x 2. So, x 1 should be taken as 50% of the total x 1 plus x 2, and here also it should be taken as 50% of x 1 plus x 2. Then for class B, which is again normal starting torque, but low starting current, it suggests that you should use this as 0.4 and 0.6, and similarly other things are given. So, I will not get into it, but there are 0.5, 0.5, 0.5, this is the most common, and then one is 0.3 and 0.7. So, these are the empirical distributions which are given. If you know this according to your class, and if you put that here as accordingly, that what is the ratio between x 1 and x 2, you substitute, then you can write this itself in terms of either x 2 dash, and then if you open it up, this will become a quadratic equation in x 2 dash, then you will get x 2 dash. Once you get x 2 dash, you will also get the x 1. So, we will do one numerical example in the next class.